In our lesson today, we are going to discuss extraction of iron metal from its ores. So iron has three common ores: the siderite, magnetite, and lastly hematite. Now hematite is the main ore of iron. Now hematite as well as magnetite tend to be used in the extraction of iron. Now this is for two reasons. Number one, these two are abundant. And number two, they contain a high content of iron as compared to siderite. But if siderite was to be used for the extraction of iron, then it needs to undergo decomposition first. This simply means that the iron 2 carbonate, siderite, needs to be heated under high temperatures to cause it to decompose. So it decomposes to form iron 2 oxide and carbon 4 oxide. So decomposition of the iron 2 carbonate leads to the formation of iron 2 oxide plus carbon 4 oxide, as seen from the following equation. Now, iron 2 oxide is an unstable oxide. So what happens is that it reacts with oxygen in the surrounding, leading to the formation of iron 3 oxide. Now, if you want to look at the formula of the iron 3 oxide, you will note that that is simply hematite. Now, once iron 3 oxide has been obtained, then extraction of iron can proceed. But for the cases of hematite and magnetite, these steps are not done. They are unnecessary because already we have the iron oxides. Okay, now let us discuss the extraction process. So let us assume that whatever ore we have right now for this process is hematite, which is iron 3 oxide. Now, hematite is combined with coke, which is simply carbon, and limestone, which is calcium carbonate. This mixture is then fed into the furnace from the top. Now, I want to talk about the structure a bit. We'll come back to the reason why coke and limestone are added, but first let me mention something regarding the structure of the furnace. Now, the furnace is a huge structure. It's around 13 meters in height. Can you imagine? Now, the outer structure is made of steel and it's surrounded by bricks made of magnesium oxide. Now, these bricks provide a heat-resistant layer. Now, the reason why this is so as to minimize the amount of heat that is lost to the surrounding. So this ensures that optimum high temperatures are maintained within the furnace, and these are important for the reduction of the iron ore. Now, another thing I'd like to mention is that on the lower levels of the furnace, you'll find that there are openings that let in hot blasts of air. Now, this is air that is at a temperature of between 800 degrees Celsius to 1000 degrees Celsius, so quite high. Now, let us go back to the mixture that I had previously mentioned. So, our iron ore is mixed with coke and limestone. So, I'll be discussing the function of each of these three. Now, limestone is calcium carbonate. On heating, it decomposes to form calcium oxide plus carbon 4 oxide. Now, calcium oxide is very important in this. And the reason is because you'll find that a lot of the iron ores tend to contain two impurities. Okay, more than that, but there are two main ones that are of note. We have silica, which is silicon 4 oxide, and we also have aluminium oxide. Now, calcium carbonate plays a role in removing these two impurities. So let us write down the equations and I'll be discussing using the equations. Now, silica is silicon 4 oxide. Now, this is an acidic oxide. So it easily reacts with calcium oxide, which is a basic oxide. Now, this leads to the formation of calcium silicate. Aluminium oxide, on the other hand, is an amphoteric oxide. That simply means that it reacts with acids as well as bases. So it also easily reacts with calcium oxide, leading to the formation of calcium aluminate. Now, those are the equations. Now, I know on first sight, these equations can seem intimidating to a student, but I'm going to break it down to you such that you're going to find that it's very easy for you to remember how to write these equations. Now, let's start with the first one. Calcium oxide. Calcium has an oxidation state of 2. So oxygen also has an oxidation state of 2. So they simply cancel each other out and we end up having calcium oxide. Now, silica is silicon 4 oxide. Silicon 4 oxide, silicon is written as such. Silicon will have an oxidation state of 4, silicon 4, Oxygen in most compounds tends to have an oxidation state of 2. So these, to simplify them, we get 2. And then of course, the last step is switching. So the 2 comes to the oxygen's end and we end up having SiO2. So SiO2. Now for our final compound. Now this is the easiest part. Whatever atoms we have on this side, whatever we have on this side will simply be transferred to the other side the way it is. So we have one of calcium, one of silicon, and then lastly we have 3 oxygen atoms. There we have. So calcium silicate. Now for the second one, so calcium oxide reacting with aluminium 3 oxide. Now aluminium has an oxidation state of 3. Oxygen has an oxidation state of 2. So these of course switch. So 2 moves to the side of the aluminium, 3 moves to the side of oxygen. And our chemical formula is Al2O3. Now, again, as with the first equation, we are simply transferring whatever we have on this side to the other side. So, calcium, aluminium, these are 2, and oxygen, 3, 4. So, we have our calcium aluminate. Now, these 2 compounds form slag. So, slag is just tapped off as a waste product. Now moving on to the next one, which is coke. Now coke is simply carbon. Maybe just to remind you of what we're doing right now, I'm simply mentioning the components of the mixture that was added to the top of the blast furnace. So this was the hematite, the coke, which we're now going to discuss, and lastly the limestone. So I'm mentioning the role that each plays during the extraction process. Now for the coke. Coke is carbon. Now within the blast furnace, there are very high temperatures. Now these high temperatures are as a result of, number 1, the blast of hot air that are fed into the furnace, and number 2, because of some reactions that take place within the furnace. This is something I'll mention right now. Now carbon reacts with oxygen to form carbon 4 oxide. Now in case you're wondering, where is the oxygen coming from? Now remember I said that at the lower parts of the furnace, there are openings that are located on the sides. These openings let in hot air. And remember, the hot air is at temperatures that are above 800 degrees Celsius, specifically between 800 to 1000 degrees Celsius. Now, of course, air contains oxygen. So carbon reacts with oxygen to form carbon 4 oxide. Now, this is an exothermic reaction. So when we talk about exothermic reactions, these are simply reactions that evolve heat energy, that release heat energy. So you find that because of the presence of the blast of hot air, plus the heat energy that is released from this reaction, the temperatures on the lower part of the furnace are usually extremely high. They go as high as 1600 degrees Celsius. Now, carbon 4 oxide, being a gas, rises up. So when it rises up, it encounters hot carbon, hot unreacted carbon. So carbon in this case acts as a reducing agent. It reduces the carbon 4 oxide to carbon 2 oxide. Now again, this is very important because carbon 2 oxide is an excellent reducing agent. So both carbon and carbon 2 oxide act as reducing agents. This simply means that they are responsible for reducing the iron 3 oxide to iron metal. Just a note, carbon 2 oxide is a better reducing agent than carbon. And the reason because since it's a gas, it provides a larger surface area that comes into contact with the iron oxide. Now, as you can see from the following equations, iron 3 oxide is reduced by both carbon and carbon 2 oxide. And the end products are iron metal and carbon 4 oxide. So this iron metal is molten. Now the reason why it's molten is because as it moves downwards, the temperatures that are on the lower part of the furnace tend to be extremely high. So they ensure that the iron remains molten and it's easily tapped off. So just something to note, both the slag, which contains calcium aluminate and calcium silicate, together with the molten iron, are collected on the lower levels of the furnace. but the slag has a lower density. So that means that it floats on top of the molten iron and is collected separately. Now for the next part of our lesson, actually for the last part of our lesson, I would like to go briefly through the furnace, and my focus will be on the different temperatures that are found within the furnace. So here we go. Now as you can see, on the lower parts of the furnace, we have the highest temperatures. And this is because of two reasons. Reason number one, at this point, we have openings that let in hot blasts of air. Now, this air is at a temperature that ranges between 800 degrees Celsius to 1000 degrees Celsius. Now, another reason that is responsible for the high temperature is actually the exothermic reaction that occurs at this point. Now, which exothermic reaction am I referring to? That between carbon and oxygen, leading to the formation of carbon-4 oxide. Now, this is exothermic, so it releases heat energy. So this, together with the hot blasts of air, leads to temperatures that are as high as 1600 degrees Celsius. Now, as we move to the middle part, you'll find that the temperatures at this point are lower. The reason is because at this point, the reaction which is responsible for the formation of carbon-2 oxide is taking place. So at this point, carbon is reacting with, or let's say reducing, carbon-4 oxide to form carbon-2 oxide. Now this reaction is endothermic. So what is happening? Heat energy is being absorbed from the surrounding. On the upper parts of the furnace, the temperature falls even further to around 700 degrees Celsius. But this is where reduction of the iron 3 takes place. So this brings us to the end of our lesson. Thank you for keeping me company, and please don't forget to tune into our next video where I'll be going through past KCSE questions on extraction of iron. See you there.